I think at this point we are ready to talk about system level simulations. So this is one of the simulations that was set up using SolidWorks. And what we are actually having here is we don't have to worry about what type of building this is. Let us just say that this is some type of a building. You have individual rooms here, and you have basically a air handling system here, right? And you have these ducts which basically take air through different channels, and it's basically sending air to each and every room. So what you can do is, if you solve the mass equation, the continuity equation, the momentum equation, the energy equation, and the turbulence equations, which is called as the turbulence model, then you will be able to predict accurately, if your mesh is correct, what is the temperature and what is the temperature distribution and what is the temperature disparity in the room. So these are some things which you can do very easily with simulations, and they're quite accurate. So for example, if you feel like in a particular room, you feel like in certain areas it's hot and certain areas it's cold, that means the incoming air is not getting well mixed, right? So in that case, you can actually use CFD to maybe come up with clever solutions so that you diffuse air in all directions and you keep on oscillating this process to get a uniform mixture, right? And you can mathematically calculate this discomfort by calculating the standard deviation in temperature. Meaning, if you, again, this might be a bit technical at this point, but what you can do is, in this particular room, you can take the temperature at each and every point, and if you're calculating standard deviation, if the deviation is very high, that means that there are certain areas in the room where temperatures are higher than the mean or lower than the mean, right? Which is bad for you. You don't want that. Typically, if you need a comfortable environment, the temperature should be uniform, and your cooling system can be designed so that you achieve that. And this is what you call as a system level simulation. And finally, and here's an example for this. So let me just play this video and hopefully, so this right here is what you call as thermal management in a data center. And to be specific, does anyone know what type of containment system is being used here? Any guesses, guys? I know that this is a tough question, but if you can answer, that would be awesome. You can see that there is high temperature here, and high temperature here, low temperature here, and low temperature here. Does anyone know what the system type is? Aisle type containment, exactly. But aisle type containment doesn't make sense. It's actually aisle containment. Yes, you're right, Ajit. So this is what you call as the hot air containment and cold air containment systems. So hot air containment and cold air containment, HVAC and CAC systems. So why is it called like that? And what is the idea? So for example, these here, right, these black boxes are nothing but computers. So these are called as rack type computers. So here, this is not a single desktop like what you have. This is a rack. It basically looks like a bookshelf, but instead of books, you actually have computers which are horizontal in nature. They have an horizontal architecture, and the computers are like this. Now, the way the computers are aligned is you actually have cooling coming from the underneath, from the floor of the data center. Cold air is sucked into the temperature into these computers, and because of the processing, hot air comes out, right? Because if your computer is running for a while, it's going to become hot, and you will have hot air. Similarly, the next row of data centers are set up such a way that the hot air comes this side, and cold air is taken inside, essentially making this entire gap, what you call as an hot aisle system. So this is called as hot air containment. Why do we do this? Well, the answer is actually quite simple, right? So what happens to hot air? Does it actually rises or does it settle down? What happens to hot air? Does it go up or does it come down? It rises, right? Because of buoyancy and because of lower density, right? So what you do is in the hot aisle containment system, right above in the ceiling, you create a duct fan, which basically sucks the air. So this way you're effectively removing heat. Similarly, cold air settles down, and cold air is basically in this particular space long enough for it to be sucked in by the computers. So the hot aisle containment and cold aisle containment system is a very standard system that people use for thermal managing their data centers. Now, as far as cooling is concerned, you don't see it here, but this particular case uses something called as the raised floor architecture, meaning the cooling air contains a duct underground and cooling air comes from the ground. It's actually pumped in, right? And these type of devices or these type of systems can be researched primarily. It's like forced convection. Yes, that's correct. So these type of devices can be researched, or these layouts can be researched mainly through computational fluid dynamics. Why? Because you need to understand that, for example, Facebook or Google, right? The calculations that they are running in these type of computers, the queries that they are running in these type of computers is worth way more that they cannot use it for testing, right? So they have to make sure that they limit the number of test cycles that they do. So most of their work that they do is done using computers. So they use something called as Mentor Graphics. They use Mentor Graphics products or ANSYS IcePack to basically simulate something like this. But you can also do this in OpenFOAM or Convert CFD fairly easily to get an idea about these type of problems. The other type of what you call simulation that you can do is called as reduced dimensional models. So here the idea is very simple. These are all 1D models. These are mainly designed. What are some of the simulation softwares, Kedar? You can use Convert CFD. In fact, like I said, in the next few minutes, I'll be talking about the course that we have on HVAC system analysis that I teach, where we are using SolidWorks flow simulation to design all of these things. Similarly, you can use Converge, you can use OpenFOAM, you can use ANSYS Fluent, you can use ANSYS IcePack, which is more preferred for these type of problems. It doesn't matter because these simulations are actually quite easy to perform. The thing that is actually complex is when you're simulating, your pumps or moving parts. That is when you need specialized CFD software. If there are no moving components, pretty much anything can be used. Skill-Lync can be used. Skill-Lync can be used if you're doing reduced dimensional models or if you're developing control systems. What does that mean? So let us say that this is your space where you are trying to maintain cabin comfort, right? And let us say that I give you real-time temperature data, right? So for example, let us say you are in a room. Let us say you are in a room and then 20, it could be your office room, right? Or it could be an auditorium, it could be a conference room in your college. Just imagine this. Let us say that 20 or 30 people are coming in. Because of that, the temperature in the room is going to increase up and down, right? Let us say you monitor this data. You put a temperature data and you get this temperature as a function of time. You can feed that into a Skill-Lync model and you can see how all of your systems react, because your entire control system can be built in Skill-Lync or MATLAB or even Octave or pretty much any programming language. And you can see how your system reacts to these temperature changes, like how long it takes to react, right? So for example, if there is a 3-degree change in temperature, how long does it take for the temperature to come back to normal? For that, reduced dimensional models are very, very good because these are super fast. You can run them in real time, meaning you can run them in real time and you can also run them at real time multiplied by a scaling factor or multiplication factor. So these run very, very fast. You can do this in your laptop. Whereas if you are running a simulation like this, like the data center, it takes a lot of time. It looks like the graphical programming lab view. Yeah, well, sure. A lot of softwares have these type of interfaces. You can pretty much, lab view is also fine. You can do system level simulations in a lab view as well. So with that, guys, I would like to thank you all for taking the time to attend this workshop. Hopefully you learned something about HVAC systems and you learned how different components in your typical HVAC simulation systems are simulated using computational fluid dynamics.